Hi everyone, welcome to Calculus 1. We're going to be spending a lot of time this quarter working on slopes and rate of change. So ideas like how fast is a car moving, or how fast is the price of a stock changing, or how quickly does your salary increase per additional year of schooling. Those would all be rates of change. And again, that's what Calc 1 is all about. So we're working our way towards this idea of the derivative, which tells us how fast something is changing at one very specific instant in time. And that's actually kind of a tricky concept. So it's easy to say, well, if I look at a range of times, I can figure out on average how quickly something was increasing. But to say exactly how quickly it was increasing at an instant is a tricky idea mathematically. It totally makes sense, right? If we're talking about how fast a car is going a certain speed at every instant in time. But actually measuring and calculating that, the way that happens on your speedometer is your car would calculate, okay, in 3 seconds I covered this much ground, and that could be converted to a speed in miles per hour, which is actually an average rate, I'm sorry, not an instantaneous rate. So that's what Calc 1 is headed towards. This very first section we're going to work on is just a little bit of review to get us started thinking about that again. So the big ideas I really want to focus on here are how well do we understand slopes and rates of change, and are we good with our function notation? Those are the key tools for the first part of Calc 1, and actually for all of Calc 1. And then the other big thing is going to be really good, careful algebra skills. There's a lot of messy algebra that we're going to run into this quarter. Okay, so very first thing I want to mention is average rate of change of a function. So you may or may not have talked about this in a pre-calc class. I know I talk about it in mine, but even if you haven't talked about it before, this formula should be somewhat familiar. So I just want to talk through it and make sure you understand my notation and that you understand why this formula should look like something familiar, and we'll relate it to the graph as well so you're picturing this correctly. So our definition here, the average rate of change of function f from x equals a to x equals b. This first part here is just basically an abbreviation for all of that. So this is just for convenience, since we're going to be doing a fair amount of average rate of change early on in the quarter. We're going to use this shorthand. So AROC is the average rate of change, and then this is just interval notation. So we're looking for the average rate of change on the interval x equals a to x equals b. And the way you'd calculate that is you'd take f of b minus f of a, and you divide all of that by b minus a. So we know this b and this a are x values. Let's go ahead and look at our picture. Let's say this is a and this is b. It would be fine for these to be in opposite order, but we'll just make it that way so it doesn't mix us up too much on the picture. And then when you plug b into the function, you should get a y value. So this f of b right here is going to be the y value when x equals b. So let's see, if we went up to the curve, there's our point. So this point is b f of b. And what f of b actually is this whole length right here. That's what f of b is. A y value is a vertical distance from the x-axis up to the curve. And similarly, an x value is a horizontal distance from the y-axis to wherever we put this tick mark. So a lot of people see this b tick mark and they just think, well, that's what it means. It means that's where my tick mark is. But what it really means is your tick mark is b units away from the y-axis. And then similarly, f of a, we would plug a back into our function and we'd get our output, which would be our y value. So this is the y value at x equals a. That's my f of a. And this point is a f of a. And then if we're trying to visualize what a is, it's this little length right here. A is how far from the y-axis your tick mark is. So what we're really doing in this fraction is we're taking the change in y. So the y value at x equals b minus the y value at x equals a, f of b minus f of a, is how much your y value has changed by. So looking at the picture, I want to take this y value f of b, and I want to just subtract off f of a, and what I'll be left with is this much length, that right there. So this is my f of b minus f of a length right here. Okay, so what we're getting on the top of this fraction is how much our y increased or decreased by. In this case, it was increased, but it would work just as well if it was decreased. And then for our x values, it's very similar. We want to picture this as b is this entire length right here, and a is this length right here. And if we subtract the a from the b, it's going to wipe out this part, and we'll just be left with this length right here. This is b minus a. So when you do that subtraction, subtracting two lengths, you get how far apart they are. And depending on the order, b minus a versus a minus b, it'll give you the same number. It's just that one will be negative and one will be positive. So this right here is our b minus a, or we could even draw it up here. This is the same length. Okay, so we're taking a vertical distance, a rise, and we're dividing it by a horizontal distance, a run. So what average rate of change is really giving us is a slope. But it's not, we wouldn't call it the slope of a curve. That's why this gets a fancy name. Lines have slopes. Slope is the constant rate of change of a line. Lines always have the exact same rate of change. But curves don't. Curves get steeper or less steep, and the rate of change will be different depending on what you're looking at. So what we've just done is found the slope of the line connecting those 2 points. Okay, so there's our line. And that is called a secant line. When you take 2 points on a curve and you draw a line between them, you get your secant line. I'm going to call that L. And this expression up here is giving us the slope of the secant line. So this entire thing is the slope of L. So when you calculate the average rate of change of the function, what you're basically doing is saying, I'm going to pick 2 points on this curve, and I'm going to draw a line that connects the two. And if I do a good job of choosing, that line is going to do a decent job of approximating how steep the curve is. And we'll say that the slope of the line is the average steepness of the curve, the average rate of change. So it's not perfect. The curve is a little steeper over here and a little less steep over here, but it averages that out and it does a decent job. So that's what average rate of change is all about. So the formula should be easy to remember because it's just slope, just rise over run. So find your 2 points, rise over run. And then the meaning I want you to really focus on is this slope of a secant line business. A little bit of vocab before I quit on this. This thing is also called a difference quotient. And this is going to be a huge part of our work early on in Calc 1, trying to figure out rates of change. We will use the difference quotient all the time. There's a slightly different version of the formula that we'll see, but this is also a really nice one. This average rate of change is our difference quotient. Okay, so I will continue with examples, but that's a really important idea that I want you to keep in mind as you're working through this. Thanks for watching.